Hello, we've got a quick update on the DMOC adapter. I am actually still working on it, contrary to popular belief. We have here serial number 4 and serial number 5. You'll notice there's a difference, REV B versus REV C. So a couple changes that have been made. Had a beta tester that wired up the brake switch, and not quite sure what happened, but it looks like an inductive spike was able to get in the system and actually do some damage. So that the changes between the two are to remedy that situation, or hopefully protect against that. So one of the part of the thing that changed, essentially the relay back here, this relay is what controls the brake lights. It was actually repurposed. The original Solectria motor controllers that this copies, the brake light was controlled by the drive. So this used to be the relay that controlled a line contactor to actually switch it between delta mode and Y mode, but I've never actually ever seen that wired up on anybody's vehicle. So it got repurposed for the brake light because the DMOC645 does not have a brake light output on it. So, unfortunately, that was connected to the isolated power supply. So the 12 volts that this outputted was not the battery, it was the isolated 12 volts coming from the isolated power supply here. And that bypassed all the front end protection. So, if it's controlling a relay and it opens that up, like a brake relay, like this isn't technically, it could be, but I wouldn't recommend using this to drive a brake light directly. You want to run that through an actual automotive relay. And that relay lets go, you get a big inductive spike, could cause damage, and it may not have been that. It had been running for a while, and then there were some changes made to the vehicle, and then all of a sudden started having problems. So it could be something else. Could have been an inductive spike on the water pump, or if you have a water pump for a cooling system, or power windows, power steering, door locks, if you have automatic door locks, it could have been anything. So we want to protect against that. So one of the changes that was made, well, essentially what happened is it came in through here, through the connector here, and it boogered up the output of the switch mode supply, and actually caused these guys, one of these guys, these are Schottky diodes, they were rated for 60 volts, and it caused one of them to fail shorted. And when that happened, the current limit circuit current limited, but the current limit was set to 2.2 amps. So it sit there and just pumped 2.2 amps into a dead short constantly, and that caused the little transformer that's on there to, of course, burn up. So, focus. You gonna focus? Focus? Okay, it's not gonna focus. Anyways, you can see it's... Oh, there it goes. There. It got burnt up, and this ended up being dead shorted eventually, and then, yeah, it all just died. So, to remedy that, REV C, these go from 60 volts to 100 volts. And that doesn't seem like much of a difference, but a 60 volt Schottky diode in this configuration of the switch mode supply, if you had a 30 volt spike, that would, because of the way it operates, you would actually see 60 volts across each diode as it flips back and forth. And so 30 volts is not unheard of in an automotive spike. You get 30 volts, that would result in 60 volts exceed the breakdown of the Schottky, and it would die. So, by going to 100 volt Schottkys, that allows it to handle up to a 50 volt spike. The other main difference is, on the other side here, flip these over, the transorb, which is down in here, has been lowered on REV C. It is now a 15 volt standoff, 18 volt conduct. So the old one was higher voltage than that, so that should protect the front end better. However, this spike, I believe, came in not through the front end, but through the way the brake relay was connected up to it in this particular vehicle. So if you'll notice, there's this little red wire going across here, and this relay looks a little funny. It's zip tied in. What I did is I went and took before, like I said, the relay was connected to the 12-volt isolated power supply. Now on here, the 12-volt relay is actually connected to vehicle 12 volts. So there's no longer a way for any of the isolated power supplies on here to be exposed outside of the realm of the board. So that should protect from any spikes or anything that could damage it while it's running. So I think this is, again, this was originally not designed for this for the brake light. It got repurposed, so it wasn't designed to handle that. But now it is, and you can see 12 volts where it comes in, goes over, and then I've took a wire wrap socket to get it off, because the power was actually connected in through the ground plane. This is a 4-layer board, so there is a power and ground plane, and unfortunately it was connected to that, so there wasn't any traces to cut or anything. So I had to end up go ahead and run this wire all the way across to get 12 volts from the battery, or from your DC to DC for converter, not the onboard one, but the one that's in the vehicle 12 volts, or 13.8 volts, whatever it's set to, and that'll allow that to go through over here. Now if there are spikes that are greater than 18 volts, the Transorb will take care of those, and we should be good. Should be pretty protected. That should be more than enough. I believe that's the only changes made to it. I did change some of the code so that if it gets stuck to where it's pulling more than 2.2 amps for a certain amount of time, then it'll shut down the power supply. It'll turn on the LED here red, saying, hey, I've shut down because of an overcurrent situation. So it'll protect it better. Probably should have been in there in the first place. But yeah, so hardware-wise, that's the difference between the two. Not that much going on there. And then software-wise, there's been a few improvements. I've actually got this DMOC adapter is actually hooked up and running. It's on the debugger. Ignore that. It's hooked up to the old test box here. If you kind of look down in here, if I get the angle right, you can kind of see the little green LED flashing down there saying that I am connected to it. You can see my laptop over here is connected to it, and if I move my mouse down here, you can see if I mouse over, it says that I am connected to the DMOC. MAC address ends in FEE6, so we're connected to that machine over there, or that one that's running. And you'll see it's got this little graph on here. This is going to be what I'm using for the throttle map. So if I go and move the pot on here, you can see it moves the... Can I bring that over? Oh, the cable's too short. Let's do this. Well, here, let me make it bigger. Well, here, I'll show what's going on in here first. So it's kind of hard to do with holding both the cell phone and the graph here, but we'll do it. We'll make it work. So you can see I'm actually running this locally on my machine, although it could have easily been served from the DMOC adapter, but I just don't have it on there yet. It's easier to edit on the laptop. So one of the things you can do is you got your wire brake lines. You can see, like, as you move your mouse over the different points, it highlights them so you can grab them. So if you wanted to grab this and adjust the wire brakes, you can go ahead and grab them. And what that does is if I were to get down here and I go below that, it would obviously kick out. And it's a safety system, so that if you get too low a voltage, it'll kick out. You can also see that at this point I've got 2 dots on here, right? And one of them is the real dot, or your proposed change, and the other one, the gray, is where it was last positioned. So I kept that in there. It's really just for me, but it's kind of neat. It's actually kind of useful. So when you move the part, or move a parameter around, it gives you where it came from, so you can say, oh, did I move that dot? Yeah, I actually did. So the same thing can be done over here. So this is some random graph I had in here. So you can see that that's now moved and gives you, up here's the actual counts. It goes all the way up to 65,535, 16-bit. So down, all the way down here is 0. And then, of course, below that is 0 volts, and all the way up here is 5 volts. And yeah, so let me move that back around over here somewhere. So another thing you can do is you can deadband over here, and we can highlight that point, and you can move your deadband around. So if you want like a huge deadband, you can have a huge deadband in there. And you can see when I mouse down on one of the dots, if I click it, it's really hard to do looking at the cell phone screen while I'm recording this. But you can see that it draws the little crosshairs, and you'll be like, oh, that's kind of neat, but not really useful. But if you're on a tablet, your finger covers up the dot, so that draws the crosshairs for you, so that you can actually see what you're doing. But yeah, you can come in here and move all your dots around. You can see everything's all updating real time, so it drags the. So you have the old and the new, and then they go back together, you know. So that's kind of cool. I've spent way too much time playing with this. I think it's cool, but I'm also slightly biased. But one of the things it lets you do is you can build. I mean, a lot of people run linear, and the old Solectria vehicles actually don't have a linear pot in them, linear throttle pot. They actually have a. It's actually cubic, and so what you do is you end up having. Your points actually end up looking more like this, where you have it's very slight here, and then it gets more and more and more and more and more until you're up to full throttle, right? Or in this case, this is regen braking, so that'd be 100% regen braking. Oh, I should mention this before I get into that. What I've done is I've nominalized the system. So before it was hard-coded from my dad's Mini Cooper. That made it difficult to make changes because the throttle range that was on there was set up specifically for his car, and that converted over to torque I mean, that was it. There was no other, it was all hard-coded in there. You have to excuse me, I still have a cold. And my voice is starting to go. You'll see over here, your output is 1, which is 100%, and -1, which is -100%. So, and in the middle here is 0. And what that does is it's now nominalized, and then of course on here you have 0 volts up to 5 volts. It's now the system's now nominalized to essentially plus and minus 1. So this will be the throttle map setup. So you can get your throttle exactly mapped the way you want it, get it nice, perfect, everything like that, independent of torque. There'll be another graph that you can go change that takes in plus and minus 1, and that develops how much torque actually gets sent to the motor controller. Now, I decided to break everything up into little blocks so that if you want to adjust the torque curve, one of the things I was planning on doing was RPM versus torque. And that allows you to adjust for people that have automatic transmissions or manual transmissions that have certain torque limits at the lower RPMs, or you don't want to bust a shaft off. You can actually go in there. I mean, yeah, it's really great to be able to mash it and spin the wheels and everything, but it's actually really inefficient. And especially if it's wet out, you can have a switch to flip between modes, so you can get traction, no traction, things like that. So it'll all be 100% configurable however anybody wants to do it. And that's the reason behind it, is to do that. But anyways, like I was saying, the Solectria vehicles, they actually have it's not actually a linear curve, but it's more, I wouldn't call it exponential, I'd call it, well, I guess it's technically exponential, but I would call it cubic. It's really hard because I am looking at this little tiny cell phone screen while trying to grab these points. But anyways, yeah, you could put whatever curve you want in there, and you can see the new stuff, updates, and it's really cool. Now, eventually there'll be a nice little button where you can click and save it and everything. Right now it doesn't. It's just updating. Then if you come down here, you've got, these are all the actual raw points here. Let me make this bigger. Oh, that's another thing I should show. It does actually dynamically rescale It took forever for me to do. Whee. If my laptop had any processing power left, we could make it really big. Boom. That's probably what I should have done originally. But if you scroll down here, you can see all the little points. I got the raw values, and then the voltage, and all the different locations where the wire breaks are. So this table, yeah, it'd be nice eventually you'd be able to come in here. So this is the original table. That's what's drawing that gray, and then this is the current active table, or I call it modified. And you can type in. Eventually, you'll be able to come in here and type in the values if you wanted to, and all of this gets saved in a comma-separated file. So. Although it could be modified through that, you could just go open up the file in Notepad and edit it. If you do that, there's some more danger there. I'll have to go and but I'll have a validator in there, so it should be safe. It should be fine. But you can do crazy things that way. You can have discontinuities. Actually, I can show you that on here. This won't let you, like, I can't drag a point below another point, so it sets the bounds of the next door neighbors, because that should never happen. It has to be a one-to-one mapping. You can't have, you know, random points in there that wouldn't, you know, have a discontinuity or something like that in there. So I got that. Let's see, what other neat things are there. I think that's about it. Same with the wire break. It won't let you drag it beyond that point down there. Yeah, what else? Let me think here. What else? Oh, I had questions. Some people, this obviously, you can see the type here. It says single track. Oh, wait, here, I wanted to show this. So if you grab, like, say, this is the first point here, so it'll be like one of these down here. And you can see when I move it around, it updates it in the graph real time. So that's kind of cool. Updates both the raw value position and the nominalized position or value there. So yeah, what else was I gonna show? Let me think here. Oh, yeah, I had some questions about, like, say you have. So this is obviously set up right here for, it says type 1 single track pot. You can have a dual track pot, otherwise known as the Hall effect sensors that send out two values. I'll plot both of those on the screen here. It'll actually be a little bigger circle inside a little circle, so you can see that. And then I'll give you error bars that you can adjust, so that it's another safety method or mechanism. So if you have a Hall effect throttle and it gets out of spec, you lose one of the tracks on that, then it'll of course throw a fault and shut down. So it'll fail safe. Let's see, what else. What else was I gonna say? You can also have it be, you can have a separate throttle and a separate brake. I know some people like that. Me personally, I like having everything on the throttle pedal, so when you get past here, you're now regen braking. You could do the same thing. You could drag these points all the way down over here to the corner, and then set up like a regular vehicle would have some kind of what's it called? Kind of like a like engine drag, I guess, is that the word I'm looking for, or transmission drag, or whatever. So you could set that up so that if you say, hey, I want it to have just like a little bit of engine drag. So yeah, you can come in here and go, and then when you let up off your throttle, you'll come down and it'll be you know, it'll just only command you know, 10% negative torque to get that, you know, combustion engine kind of drag when you let off the throttle, but you're not pressing the brakes. You know, you start slowing down, even though, you know, it'll actually regen, but it's just a little bit. So that lets you take care of that. Let's see, what else do I want to show you? Yeah, I could show you how accurate it is. I guess that's kind of interesting. So right now, what are we reading here? 0.923 volts. This is gonna be really hard to do here. But we'll come over here and grab my meter. And something just fell on the floor. Because I had somebody ask me about how accurate this thing actually is. It's pretty accurate, but even if it wasn't, you can adjust for it in the graph here. So I gotta remember, what did I just say? Hold on. We're at what's it say there? 0.923 volts. 0.923 volts. So go ahead and stick that in there. Oh, this is gonna be really hard to do. I think I can get it. Can you actually see that? What's it say? 0.923 volts. 0.294. No, 0.923 or 4. Yeah, it's split between 3 and 4 on the last digit. Okay, what are we doing over here? So it's probably doing the same thing. It's be flipping between 0.9234. Yep. So I'd say it's pretty accurate. It's working. It's doing what it's supposed to do. Which is, it doesn't seem like that's impressive, but on here it's actually going through, it's all optically isolated. So that's coming in through here, and it goes through, I do a full analog optical isolator. So there's 4 analog channels on here, and those are these guys right here. They're passing it through, and then it gets re-amplified on the other side, and then it gets over to the micro. The micro is onboard A to D converter. So I don't know. I'm amazed it's that accurate, but it does actually work out to be that accurate. I was actually planning on having a table in there that you could adjust to make sure it's perfectly accurate, but it's actually spot on. So I haven't found the need to actually do that. Might end up doing it at some point, but I don't know. That might be later for people that want to adjust that kind of stuff. So yeah, what else do I got? Oh, I updated the I don't know if you noticed, but every once in a while it pauses, and it's because Adobe. It's going out checking for updates and doing all kinds of crazy stuff. I need to go figure out how to keep that, because despite the fact that it has local access only, everything still tries and goes out. Windows is going out, Microsoft's going out, Google, if you looked on my back here, I'm logged in, so Google is going out like all the time, trying to check for my email and stuff. So it's crazy. If you run Wireshark, you actually see like all this crazy traffic going across. I should have used my tablet to demo this. That would have been a lot easier. But that doesn't seem to hit the internet as much when it knows it's got a local connection instead. But anyways, this is the wiring diagram. I got all this kind of set up, threw some stuff in here. Like I was talking about the analog things, I've got my block diagram of it. It is an analog isolated A to D converter. Everything's isolated. All the inputs and outputs are all isolated. So that's cool. Got all that hooked up, and then I've got the wiring system for wiring up the high voltage contactors, pre-charged circuit, and all that kind of stuff. And then all the extra random spare connectors that are on there that have uses, but no code's been written for them yet. And then this is the actual wiring diagram for the took up the DMOC 645, and it's all available on the website. So yeah, that's it. I think I don't got anything else going on, but yeah, that's graphing thing. I still think this is cool. This is all written in HTML5 WebSocket, and then the graph is all drawn in HTML5 draw canvas, and then all the math is done in JavaScript. So yeah, it's pretty cool. Well, I think it's cool anyway. I don't know. Anyways, this video ended up being a lot longer than I thought it would. So yeah, go ahead and end it now. Thanks. Bye.